In this lecture, we will be introducing the concept of the indeterminate form and how we handle that in the context of limiting expressions. So first, an indeterminate form is just a mathematical expression that's not definitively or precisely defined. So it's something that mathematically doesn't make sense. These are some examples of indeterminate forms. It's important to recognize these are not mathematical expressions. Each one of these symbols means something in mathematics, but these expressions are not defined. So infinity minus infinity is not defined. Division by zero is not defined. This is something, probably the one we're most used to. It would be like saying, if you have one pizza divided 0 ways. This is something that doesn't make sense. 0 over 0, 1 to the infinity. Again, all of these are not defined, but they come up in calculus when we're dealing with limits. And we have a rule that becomes very handy when they come up called L'Hopital's rule. L'Hopital's rule says if f and g are differentiable functions, L'Hopital's rule is a theorem that states the following. Suppose f and g are differentiable functions if direct evaluation of the limits in the numerator and the denominator of this limit expression yields indeterminate form of 0 over 0 or infinity over infinity, then the rule is the limit of that quotient of f over g equals the limit of the quotient of f prime over g prime. The idea here, and let's look at the case where each of these is going, both top and bottom are approaching infinity. So if the top is approaching infinity and the bottom is approaching infinity, what L'Hopital's rule says is that they're both going to this same place. And the limit of this ratio can be determined by the limit of their velocities at how quickly they are going to this place. And of course we know, if you think in terms of position and velocity, if you think of f and g as position, their derivatives would be velocity. The key thing to recognize is that this only works for these two indeterminate forms. And this is most naturally seen through examples. So a classical example for use of L'Hopital's rule is the limit as theta goes to 0 of sine of theta over theta. And we can actually see, if we try to directly evaluate this, sine of theta as theta goes to 0, that's approaching 0. And of course, theta going to 0 means the denominator is going to 0. So we say this yields 0 over 0 indeterminate form. And it's important to write it this way. A very common mistake is someone will write this equals 0 over 0. But this limit is well defined. It's something we can calculate, and we just discussed that 0 over 0 mathematically is a nonsensical expression. It's an indeterminate form. It's not well defined. So you never want to write this equals 0 over 0 because that's a mistake right off the bat. But this direct evaluation yields that 0 over 0 indeterminate form, and so we can use L'Hopital's rule to say this is the limit as theta goes to 0 of the derivative of sine of theta with respect to theta, cosine theta. The derivative of theta with respect to theta is 1. And of course we know, if we look at the graph of cosine theta, we know the limit as theta goes to 0 of cosine theta is 1. So that's a classical use of L'Hopital's rule, and a lot of times it's nice to justify it in this way, so that when you take the L'Hopital step, a person looking at your work knows that you're actually citing L'Hopital's rule after you've determined you have an appropriate indeterminate form for its use. Now you'll see here we have a picture, and this is included just to give a sense of what this limit actually looks like. So the yellow line is the 45-degree line, y equals theta, and the blue curve is y equals sine of theta. And the idea here is you see y equals theta is tangent to the graph of y equals sine theta at the origin. And the more and more you zoom in here, the harder and harder it will be to distinguish the sine curve from the y equals theta curve. And the idea is when you go all the way with theta being 0, they're the same. Hence the limit of their ratio is 1. So this is a handy way graphically to see why this works. But it's L'Hopital's rule that gets you there. Let's look at this example. Limit as x goes to infinity of natural log of x over natural log of x plus 3. And let's try to feel out what the answer is going to be. This is a useful thing to do in most limit exercises. It won't always work out that you'll be able to feel out what's going on, but it certainly helps. And in this case, x is going to infinity. So natural log of x and natural log of x plus 3 should look more and more similar. Think about when x is enormous. If x is 1 trillion, you have natural log of 1 trillion over natural log of 1,000,000,003. The bigger x gets, that extra 3 is becoming more and more insignificant. So much so that we should expect really this to behave like ln x over ln x, or 1. So that's a way that we can feel it out, which is, of course, not the same as computing it. But we note that here, that numerator is approaching infinity, and the denominator is approaching infinity. Think of your graph of the natural log of x. As x goes to infinity, the natural log of x is going to infinity, albeit slowly. But this thus yields that infinity over infinity indeterminate form. And we can thus use L'Hopital's rule to say this is equal to the limit as x goes to infinity of the derivative of the numerator divided by the derivative of the denominator. We know the derivative with respect to x of natural log of x is 1 over x. And we know the derivative with respect to x of natural log of x plus 3 is 1 over x plus 3. And now we have a limit computation like we've learned in our first calculus course most likely. And so we have a 1 over x, we have an x in the denominator, and then this x plus 3 comes up to the numerator. Or limit as x goes to infinity. Well, if we have x plus 3 over x, we can break that up. We have x over x, which is 1, plus 3 over x. And applying our limit laws, the limit of the sum is the sum of the limits, as long as each of these terms has a limit, which they do. And we know that this 3 over x term approaches 0, and so our answer is 1, as we expected when we guessed what was going on in our first step. So these are our classical examples of how you use L'Hopital's rule.